Okay, so we will continue today doing problem on chapter 20. We have introduced last time the equation that we will use in order to optimize the speed of machining, the cutting speed. We have two main criteria in general, the maximum production and minimum cost. Okay, so we will do some practice problem on this today. A high-speed steel tool is used to turn a steelwork part that is 300 millimeter long and 80 millimeter in diameter. The parameters in the Taylor equation are n equals to 0.13 and c equals to 75 meters per minute for a feed of 0.4 millimeter per revolution. The operator and machine tool rate is $30 per hour, and the tooling cost per cutting edge is $4. It takes 2 minutes to load and unload the work part and 3.5 minutes to change tools. Determine the cutting speed for maximum production rate and the tool life in a minute of cutting and the cycle time and cost per unit product. Okay, so first we should determine what is the type of operations used. So here we have a turning operation. They gave us the length of the work part, L. We will need L for the machining time because you know that for turning operations, the machining time is given by pi dl over fv. Okay, so if you remember when we worked on turning, we said that in order to compute the machining time, we should know the diameter of the work part, its length, the feed rate, and the velocity of cut. So this is L. We have the diameter of the work part is 80 millimeters. The parameters in the Taylor equation are n and c. So also we will need n and c in our calculation. They are given. This is the feed rate F. Now, concerning the operation, the operator and machine tool rate are $30 per hour. This will help us into assessing the cost. And the tooling cost is per cutting edge is $4. So for each cutting edge, the cost is $4. And the time to load and unload the work part, because you know that the total time is decomposed into several parts. So we have TH, which is the handling time, needed to load and unload the work part. It is given. And we have the machining time, and we have also the tool change time per unit product. Okay. Now, first we want to determine the cutting speed for maximum production rate. So if we go back to our formulas developed, since we are working on the criteria of maximum production rate, so we will use the following formula. V corresponding to maximum production rate, we need the parameters needed to calculate this velocity is C, which is the constant in Taylor equation. We have n coefficient also for Taylor equation, and we have the tool change time. Okay, so we should compute what is the tool change time. It can be given here. We will see in this problem what is its value. So this is how we can calculate the value of Vmax. So let us go back. So as we said, in order to calculate the value of Vmax, okay, we have first C. C is given here. We directly replace it in a meter per minute. Just pay attention for your units, okay? So here is C is used in meter per minute. We have 1 over n. N is the coefficient in Taylor formula. N is equal to 0.13. Okay. Now we just still have to, and this is here also 0.13 is n. We still have the tool change time. Okay. So we have that the time we have 3.5 minutes to change tools. So the total here we replaced in this formula. TT is the total changed time. Okay, so TT in the formula represents the total time need to change tools. This time is given in minutes, 3.5 minutes. So this is why C should be also per unit per minute. Okay, because T total is given in minutes. So replacing back in this equation, we can get the value of Vmax in meter per minute. Okay. Now, also, we have that in the computation, we have a relation. Yani, once you find the value of Vmax, okay, you can use the Taylor equation, which is V times the tool lifetime. So we have V times T to the power N is equal to constant C. So once you determine the optimal cutting speed, V for maximum production rate, you can deduce what is the tool lifetime that will give you the corresponding maximum production rate. So this is called Tmax. Okay, the tool life that will maximize the production rate. So here, once we get Vmax, all we have to do is to replace into this expression. So we get that T is equal to C over V to the power minus N. Okay, sorry, to the power 1 over N. Okay. So now this is what we did. We replaced Vmax by its value, and we have the value of C. So it's C over V to the power 1 over N. And then we get the lifetime in minutes, which will optimize the production rate. It will give us the maximum production rate. The third question is to determine the cycle time and cost per unit product. Okay, so we know that the cycle time is divided into several parts. So we have the handling time, we have the machining time, and we have the tool change time per unit product. Okay, so first, concerning the handling time, it is provided, it's equal to 2 minutes. So this is TH. Concerning the machining time, it depends on the type of operation. So here we have a turning operation. We can have any type of operation which is already covered before, and we know how to calculate the machining time for each type. So we have that Tm is pi dl over Fd. We have all parameters, so we can calculate the corresponding value. Just pay attention to have same units, so all are in minutes. Okay, so this is T handling, T machining. We still have the tool change per work part. So 3.5 minutes is the total change tool time, T total. So now we should know in one lifetime of the tool how much product we can get, the number of products we can get, okay? And we should divide the total time by the number of pieces that we can produce per tool life. So if we go back to the given, they should provide us with this number. Okay, here we don't have it, we should calculate it. How you can calculate NP? How you can calculate the number of pieces produced from the information that you have found here? Who will tell me? If you have a tool, okay, and you know its lifetime. So here we calculated together the lifetime of the tool. The lifetime of the tool for maximum production rate is given by 23.42. Okay, if I know the machining time, what is the machining time? The machining time is the time needed to produce one product. So if I know both of these parameters, the total lifetime of this tool and the machining time required to produce each product, then the number of pieces that I can produce during the whole lifetime of the tool will be the lifetime of the tool over the machining time per unit product. And this will give me what is the number of pieces I can produce during the lifetime of this tool. This is why once we have calculated the value of the total time for the lifetime of the tool And we have calculated the time needed for production of one part. Please pay attention. Who will total time for production who T handling plus T machining plus the change tool time per unit product. But here, what is affecting the tool life is just the machining part. This is why we don't divide by T total. We just divide by TM. Okay, because what will affect the tool life, what will do wear to the tool is not the handling and the change part, it is the machining part. So when we divide the lifetime of the tool by the machining time, we can get what is the number of pieces we can produce during the lifetime of the tool. And therefore, we have that the total time can be computed as TH plus TM plus T total over NP, where NP is T max over T machine. Okay, so in this case, we can get the value of the total time. Okay, and once we get the total time needed for the cycle, now also we will use these times also to assess the total cost. So now we want to compute what is the total cost needed to perform this operation. So to perform this operation, we have a handling cost. Okay, so since each part will have a cost, so we have T handling, we multiply it by the operational cost, which is here given by we have the operator and machine tool rate is $30 per hour. Okay, so here we know what is the value of T handling, what is the value of T machining, and what is the value. If you want all these have the same rate, because they didn't say that, for example, for handling you have this cost rate, for machining you have another cost rate. No, they gave you one cost rate for all. The operator and machine both have a rate of $30 per hour. So this total time should be multiplied by the rate. Okay, but please pay attention for units. Here is given in dollar per hour, while here the total time is computed in minutes. So make sure to convert to minutes. So here we should divide by 60. 30 over 60 is 0.5. So we multiply 0.5 by the total time of the operation, which is 6.37. This will give us the cost of the operator and machine, but also don't forget the cost of the tool. So you should add to this the cost of the tool per unit product. They told us that the tooling cost per cutting edge is $4. So now we should divide 4 by 6, which is the number of pieces that can be produced during this operation, which will give us the total cost per piece per unit product. Okay?
دكتور
Yes.
لا ان بي اخدناها 6 مش 7.
الان بي هي 6 ان بي هي number of pieces. انت كيف انت قصدك هون انه when we divided 6.184 you mean you should round to the لانه انت بالاخر هيدي البارت انت اذا بيطلع لك 6.18 ما فيك تقول انه طلع لي 7 pieces، فيك تقول طلع لي 6 صح؟
اوكي
بدك تاخذ الاوطى مش الاعلى.
اوكي
you disregard after the common number you get. Okay.
اوكي.
Any other question on this? Okay. Another problem. Just 1 minute. Sorry. And Anna, I selected for you some problems. Let me open the PDF. Okay. Compare disposable and regrindable tooling. This is the purpose of this problem. The same grade of cemented carbide tooling is available in two forms for turning operations in a certain machine shop: disposable inserts and brazed inserts. So here we need to select the corresponding tooling. We have two choices. The parameters in the Taylor equation for this grade are N equals 0.25 and C equals to 300 meter per minute under the cutting conditions considered here. For the disposable inserts, the price of each insert is $6. There are 4 cutting edges per insert, and the tool change time is 1 minute. So this is an average of the time to index the insert and the time to replace it when all edges have been used. For the brazed insert, the price of the tool is $30, and it is estimated that it can be used a total of 15 times before it must be scrapped. The tool change time for the regrindable tooling is 3 minutes. The standard time to grind or regrind the cutting edge is 5 minutes, and the grinder is paid at a rate of $20 per hour. Machine time on the lathe costs $24 per hour, and the work part to be used in the comparison is 375 millimeter long and 62.5 millimeter in diameter, and it takes 2 minutes to load and unload the work. The feed is equal to 0.3 millimeter per revolution. For the two tooling cases, compare first the cutting speeds for minimum cost, the tool lives, and the cycle time and cost per unit of production. Then which tool would you recommend? So in this problem, if you want, we have the criteria of selection. Yani we will do comparison of two tooling in order to decide which one to select. So here we will compare several parameters. We will see which one will have, so we will compute the cutting speed for minimum cost. We will compute the tool lives, and we will compute the cycle time and cost per unit of production. And based on these results, we will decide which tool to use. Okay. So first, in the first step, we will find the value of, so first we will perform all calculation for disposable inserts. And in a second step, we will do the same operation then to calculate V minimum and V maximum for the case of the other type, which is regrindable tool. Okay, so let us start with disposable inserts. First, we want to calculate the cutting speed for minimum cost. So also, as usual, we go to the formula sheet and we see what is the expression of V minimum, as we have done in the previous step. So we go back to the formula. In the first example, we worked on the maximum production rate. Now we will need the formulas of minimum cost. Okay. So for minimum cost, these are the formulas. You get V minimum is also dependent on a C. So first you have C, which is the parameter in Taylor equation. You have N, which is also parameter in Taylor equation. We have C0 is related to the cost, okay? And we have CT, the cost for tool change. And we have, so C0 is the operational cost if you want. And we have that TT is the total change time, okay? So now we want to use this expression to get what is the value of V minimum. So first, concerning parameters C0 and CT, okay? So we have that first for C0, which is a certain, the lathe cost, which is the operational cost of the machine, okay? The operational cost on the machine as is given here. So we have that the machine time on the lathe is $24 per minute, per hour, sorry. So also we should make sure to convert to unit time per minute. So C0 will be equal to 24 over 60, which is $0.4 per minute. Okay. Now concerning CT, it corresponds to the cost of the change of tool. Okay. So here we have that the price of each insert is $6. And each insert, okay, is characterized by a certain number of edges. Okay, so we have 4 cutting edges per insert. So the tool, if you want CT, will be the cost per, if you want per edge. This is why we divide the tool cost, which is the insert cost, by the number of edges. So 6/4, we get it's $1.5 per edge. Okay, so this is the tool cost per edge, CT, and T0 is the operational cost. And now we will be ready to compute the value of V minimum. So by replacing C0 and CT by their values in the formula we mentioned above, and having C and N also, then we can compute the value of V min. Just we should pay attention for units. So to have, should have the cost in dollar per minute, okay, and then we can get the value of V min. Now, once we get V minimum, we can compute what is the tool life that will ensure the minimum cost. So we just have to use the expression that is developed also here. So you have it here. You have a certain formula also for T minimum. So just to use it, you replace your values, you can get the value of T minimum. Okay. And then once this is done, we have already what is the tool life that will minimize the cost. So for the first type of tools, which is the disposable inserts, the tool life required is 14.25 minutes. Of course, انتو إذا عندكم several options, okay, كل ما كان التول يعني كل ما زاد التول لايف required بيصير أصعب، يعني بيصير إذا بدكم you have a higher cost for the tool، لأنه التول بالنهاية إذا أنا بعطيكم 2 tools بيعطوني same function، okay، أنا إذا بقدر أحصل على restriction أقل بيكون أحسن. يعني أنا إذا عندي tool مفروض يعيش 10 minutes بينما واحد تاني إنه لازم يعيش 20 minutes، يعني هون في constraint أكثر على تاني tool. Okay, so if they I will try to find the if you want the conditions اللي هن أهين شيء علي. Okay, so now what I still need to calculate is the cycle time and cost per unit of production, and based on this, after having the different values, we can do the comparison. Okay, so now to get the cycle time, as usual, for the cycle time, we should add the handling time, we should add the machining time, and we should add the tool change time per piece. Okay, here they gave us these different parameters. To load and unload the work, we have 2 minutes. هلا مفروض اللودينج والانلودينج ما يتاثروا بالتول، يعني it's the same time for both. Now the machining time is related to the turning operation. Okay, so we will use the formula which was developed before. So we have pi dl over fb, so we can get the machining time as we did in the previous problem. We have all parameters here, so we can compute the machining time. And once we have the tool lifetime and we have the corresponding machining time, we can get the number of pieces resulting from the operation. So here we have 8 pieces per tool, and then we can find the cost per you have the total change time 1 minute, you divide it by NP, you get the tool change time per unit product. This will give you the total time required. And now, once we have this, in order to assess the cost, as we did in the previous problem, first we find the operational cost by multiplying the total time by the C0, which is the cost per unit. And here we have in dollars, the cost in dollars per minute. Okay, so we multiply the operational cost, which is $0.4 per minute, by the total time, which is 3.72, And also we should take into account the if you want the cost per unit product, okay, for the tool. Here for the tool, okay, we have that we should take into consideration several factors. We should take the cost per edge per unit product. Okay, so here we have seen that we have the total cost of the total cost of the tool is $6. But what we need here is the cost per edge. So we divide first by 4. We get this is the cost $1.5. This will represent CT as was calculated here. This is the cost per edge. Now this cost will be divided by the number of pieces that we will produce, which is 8. Okay, so based on this, we can calculate the cost per edge per unit product, and we add it to the operational cost. We get the cost, the corresponding cost. Okay. Now, for regrindable tooling, we will perform the same calculation. What is different just here is what is concerned with the tool. So instead of having inserts, we have regrindable type. And they told us concerning the properties of it. So we have that let us see where they mentioned something about the grinding operation in the given. So these first are the properties for the inserts. Now, concerning here, they started with the properties for the brazed insert. We have the price of the tool is $30, and it's estimated that it can be used 15 times before it must be scrapped. So we can regrind it 15 times. Okay. The tool change time for the regrindable tooling is 3 minutes. The standard time to grind or regrind the cutting edge is 5 minutes. And the grinder is paid the rate, so this is the grinding rate, $20 per hour. And now we will see how this will affect the time, the cost, and the time. Okay, so we will perform now calculation for regrindable tooling. So first, concerning C0, as we mentioned, C0 is related to the operational cost. It's independent of the type of a tool. Okay, so you will see that C0 will remain the same between parts A and B. Now concerning CT will be different, because here when we calculate CT, okay, we should take into account first the total cost of the tool over the number of times that it can be grinded again. So it's 30 over 15. But also, since grinding or regrinding will take a certain, if you want, cost, so we should take into account the cost for grinding operation. Grinding operation here is given, so we have its cost is $20 per hour. So in order to convert to hour per minute, so we divide by 60 here to convert from dollar per hour to dollars per minute. And also we should multiply it by the number of minutes required for the regrinding operation, which is 5 minutes. So then we will obtain the grinding cost. Okay, so now we can say that CT is equal to the summation of these two, which is $3.67 per edge. Okay, now once we have C0 and CT, all we have to do is to perform a replacement. The replacement in the formula will give us the corresponding cutting speed. Okay, then after we get the cutting speed for minimal, if you want, for minimal cost, then we will compute the tool life by replacing in the formula. So here it's the same idea, same formula, just we have a different value of the minimum. Okay, and once we have this, we can calculate, we will move to the second step, which is the calculation of the cost. And at the end, when you want to compare, what is important for me is the cost. And when you perform the calculation, okay, you want to compare the cost per piece, okay? And because this is different types of tools. Okay, so I will not take just the tool life into consideration or the cutting speed just into consideration. What is important for me at the end is the cost per unit piece. The smaller the cost per unit piece is, the better is the option to take. Okay, so we have for the machining time also same formula. Okay, in this case we have V is different between the two. Okay, so here we have calculated the value of V. We can replace it. We have the number of pieces as usual is calculated as the tool life over the machining time. So here, for example, here you have a higher number of parts produced per tool life, which is good. But on the other hand, also the tool life is different. Okay, and at the end, you cannot just compare NP or just compare the tool life. You should compare the cost per unit product at the end. Okay, so it's true that here maybe we have a higher value of pieces per tool, but also for the tool cost is higher. Okay, and when we want to select the tool, higher the tool lifetime, higher will be its cost. So we cannot just compare the tool life or just compare NP. As what is important for us at the end is the cost per unit per piece. Okay, so we might have NP higher. So here, if you do the comparison for the second type of tooling, for regrindable tooling, you have higher number of pieces per tool. Okay, but this does not mean that the cost is lower. Okay, because the cost is affected by several parameters. It's affected by the tool life, and you can expect here, for example, that the tool life, okay, combination of tool life and the value of, because when you want to compute NP, you have several parameters affecting it. You have the tool life, and you have also the machining time. The ratio of both will affect your result. So if you do comparison here, you can see that if you just compare the tool life, you have here a higher tool life. Okay, a higher tool life means if you want also a higher cost, because to have a higher tool life, the cost you will put will be higher. So until now, you can just say that the tool life for the first case is smaller than the tool life for the second one, which means that maybe here I can be sure that the tool is more sophisticated, has better mechanical property because it can resist wear more. It has a higher tool life, but at the same time, I should also look at the other parameter, which are the machining time. If I compare the machining time here, for example, is higher. So in order to make a conclusion, I should compare first NP. And when I do this ratio, I can see that here the number of pieces is larger. So as a first look, it's good. At a first glance, it's good to do more pieces per tool, but also I should pay attention that this is not sufficient to decide. Because if I want to decide, I should take into consideration the cost and the total time. Okay, so here, if you do comparison of the total time, you will see that the total time here is higher. So the time needed per piece will be higher than the first operation. And to decide at the end what will tell you which option to take will be the cost. Okay, so here I want to calculate the cost for both, and this will be the criteria of comparison. Yeah, I cannot just look at the NP or just look at tool life. No, I should compare the cost. So now, if you compare the cost for the first part, the cost is $1.674 per piece, while for the second, it is $1.876 per piece. So I will select this option. Okay. So based on this, I can say that disposable inserts are recommended because cycle time and cost per piece are less. Okay, and I care for the time. At the end, the time is very important also. So here I have lower cost and lower time. Okay. Any question on this? Another problem A vertical boring mill. So here, for example, they changed the type. We are working now in a mill, not a turning operation. So we have a boring mill. It's used to bore the inside diameter of a large batch of tube-shaped parts. The diameter is 28 inch and the length of the bore is 14 inch. The current cutting conditions are a speed of 200 feet per minute, a feed of 0.015 inch per revolution, and a depth of 0.125 inch. The parameters of the Taylor equation for the cutting tool in the operation are n equals 0.23, c equal to 850 feet per minute. The tool change time is 3 minutes. The tooling cost is $3.5 per cutting edge. The time required to load and unload the parts is 12 minutes. And the cost of the machine time on this boring mill is $42 per hour. Management has decreed that the production rate might be increased by 25%. Is that possible? Assume that feed must remain unchanged in order to achieve the required surface finish.